So thank you very much, and thanks to all of you for joining in, so many of you. You probably haven't missed it. On August 9th, the latest IPCC report, the Work Group 1, has been released in the middle of the summer, but still had quite a few articles and general interests. So my aim here will be to sort of cover things that are present in the reports, mostly in the summary for policymakers. I would be able to do something exhaustive, but try to raise or underline some of the results, which I believe are very important. But first of all, some general comments. What is the IPCC? It stands for Intergovernmental Panel on Climate Change, and it is official UN extension. It's been there for a while. It was decided during, well, in preparation of the summit, the Earth Summit in Rio in 1992. So the first reports came out in 1990. We're at the 6th edition of this assessment report. The latest one, the full report, was in 2013. As you can imagine, there's been a lot of new research being done between, and climate change has also progressed, so that some of the results become clearer now. How does the whole IPCC reporting work? It is meant to be an as comprehensive and as transparent process as possible, where authors are selected by governments to work as draft authors and contributed authors, and they only look at results that have been published in peer-reviewed publications to ensure the highest possible scientific quality. But once the report is done, it undergoes different review processes, both by experts in the fields that did not take part in writing the reports, as well as the open society. And to give you an idea, more than 200 of the best experts in climatology were put together to write the reports, which has then been reviewed by 23 other climatologists and 23,000 and over 50,000 other experts to make sure that it really reflects the current state of the art. Remember that this is only the first part of the IPCC report, the one of the scientific basis. We are still waiting for the work group 2 looking at the impacts of climate change, and work group 3 dealing with mitigation to be published during the spring of 2022. There are also the IPCC Atlas that I will come back to later on, and some FAQ that the IPCC releases, which can be very helpful for the general public. The IPCC not only looks at what their best summary is of the current state of knowledge, but they also look at the degree of certainty, in how certain a certain result is. And you see here in this table how the different levels of probability translate into the IPCC terminology from virtually certain to about as likely as not. So as I said, IPCC has been around since the 90s, and in the meanwhile, we can't really see a strong impact, because since the first report of the IPCC has been published, mankind has emitted roughly as much CO2 as it has since the beginning of the Industrial Revolution. So there is now a sense of urgency given the results that I will be showing, and scientists as in researchers' desk, certainly hope that these results will really have an impact on policies. So very briefly, go over things we already know. We know that climate is changing. We know that the Earth is now warmer than it has been for at least 100,000 years. We know that it is, to a large part, caused by human activity. You see on the graph on the right. If you run models without any human influence, it is not possible to present the observed curve of temperatures. And to quantify this further, based on all the observations that we have, we can say that the climate of the last decades is about 1.09 degrees warmer than pre-industrial climate. And out of this difference, 1.07 can be related with a high level of probability to human activities. If we look a bit closer into what of the human activity causes this climate change, we can see that carbon dioxide is the major driver, as we knew. I believe that this report stresses even more than the previous one, the role of methane, which according to this graph accounts to about 2/3 of the radiative forcing, so the changing factor on climate. So that's maybe one point to remember. Methane has been identified as a critical issue in current and future policies. What we already knew is that climate change is not uniform. The poles in particular do warm up a lot faster than the rest of the planet. Land does warm more than air above the oceans. And would like to stress here in this picture are the lower two figures. Even though warming between 1.5 and 2 degrees might sound like something very similar, in fact, it isn't when you look at the details. So the consequences of 2-degree global warming, especially in the Nordics, are a lot more pronounced than by 1.5. But temperature is only one thing. Climate is a lot more than just the temperature. And you can see that the changes in the energy budgets changes the way the atmosphere organizes itself, and therefore have a strong impact on precipitation. And once again, you can see that the changes in expected mean precipitation are significantly larger in a 2-degree warmer world than what they are in 1.5. We can also see that the aridity of the soils react very strongly to the mean level of global warming. And look in particular how sensitive the Amazon region would be to an intense warming. And that's the next point I would like to raise, and I think it's particularly obvious in today's, in the most recent reports, where climate is not only described as a mean of a certain variable over time and over space, but when the results on extremes have been lifted. And as you can see here in this graph, it represents like a symbolic representation of different regions on Earth. And you can see that almost everywhere, the hot extremes have increased since the 1950s. And that's what you can see with a reddish color. And in many regions as well, this increase in hot extremes can be related to human activity with a high level of confidence. That's what you see when you have the 3 points. the same can be done as well with precipitation. Now with the better coverage of observation networks and with a stronger climate change since the previous assessment reports, it has been obvious that precipitation extremes have increased both in frequency and in intensity. And it's particularly the case in the upper box for Northern Europe, where we're located right now. And I mentioned the IPCC Atlas. I think this is a very good way for anyone to look through the whole wealth of observations and climate modeling that has been done to look at questions they are interested in directly, which might not be explicitly addressed in the reports. It's an online web tool, which is very easy to use. And you can see that this upper northern box fully corresponds to Scandinavia and to Stockholm, Norrköping, and so on, where we currently located. It's interesting to see that the extremes even cover Germany, and that's well, the increase in the frequency and of extremes also covers Germany, which is particularly relevant today, given the inundations that we witnessed this summer. The same thing can be seen also about the drought indexes. It might sound a bit contradictory that even though precipitation is increasing, droughts may be increasing as well. It has to do with the evaporation and transpiration by vegetation of the available water, which increases if temperatures increase. And if you look at the two regions where the coupling of this increasing trend in extremes can be related to human activity, is Western North America and the Mediterranean, both regions who particularly this summer also have experienced extreme forest fires. So this report gives, well, not talking about one particular event as such, but the fact that forest fires become more intense is in line with the results that are shown in this report. And just to underline, not only do we see that the extremes have become more frequent, more intense, and that they are related to human activity, but for any additional warming, this trend is expected to continue. And to give you an idea, if you take 1 decade in pre-industrial climate and look at its warmest daily temperature, today we're almost 3 times as likely to reach that maximum. In a 1.5 degree world, it would be 4 times as likely. In a 2 degree world, we would have what was or would have been called an extreme year in pre-industrial climates. That's the kind of extremes we would have every second year. The same thing happens as well with precipitation. It has been observed, and it's now quite quantified, that the extremes are actually increasing, and it's also indicated that this trend is likely to continue. And there you see the risk and the huge difference between a 1.5, a 2, and a 4 degree world. not only does the frequency increases, so in 4-degree world, for instance, we could have extreme precipitation every 3rd year that there was experienced only once in a decade in the pre-industrial world. But on top of that, the intensity of these extremes also increase significantly for every 10th of a degree. The same thing happens again for drought. And once again, it is not in contradiction that both precipitation and drought may increase because of the evapotranspiration that I mentioned earlier. So how does, what kind of tools and scenarios does the IPCC use to try and look at different pathways for our future? The major tool that you've heard certainly before are the SSP, the shared socioeconomic pathways. And these are fairly advanced scenarios looking at many different impacts like population, industrial and agricultural practices. And they're all meant to be realistic in their own way and consistent all along. So that's how these different scenarios can be tested and see what a future climate would look like if we follow more one or another scenario. But once again, these are not projections. So it's not like weather forecasts being able to say what is going to happen. These so these are not predictions, these are projections. If we choose a given scenario, then the climate is likely to evolve in a sort of way. If we choose a different scenario, then the projection says that temperature and precipitation will evolve in a different way. But which of the scenarios is the most likely to happen is not discussed by the IPCC. It's not the role of the body. This is more of a political aspect, and I believe it will be addressed a lot more during the COP26 meeting in November in Glasgow. So basically, 5 typical scenarios were retained to be compared. 2 of them reach net zero CO2 emissions before the end of the century. 1 reaching net zero shortly after 2050. The other one, the SP at 2.6, reaching zero by about 2070, roughly. But on top of just the CO2, all these SSPs also include consequences for other drivers of the climate change, like methane and other gases. So that's how it would look like in terms of global mean temperature. The IPCC says that it is very likely that we exceed the 1.5 limit within the next 20 years, so before 2040. In the top 3 scenarios, it is more likely than not that we exceed the 1.5 limits for the 2.6 and 1.9. But even if we do exceed it with the 1.9, because of the negative emissions overall, this would be an overshoot, and the temperature would stay below 1.5 at the end of the century. And this is what is summarized here. You can see both the best estimate, but also the uncertainty or the likeliness to be within that range. And as you can see, for the near term, all the scenarios reach 1.5. Why is 1.5 so important? If you look at the actual formulation of the Paris Agreement, the nations that signed it pledged to stay well below 2 degrees, aiming for 1.5. So it is somewhat unrigorous to claim that a scenario that would reach just below 2 degrees would be in line with the Paris Agreement. And that's why it's so much, that's why I will focus a lot on the 1.5 in the graphs to come. One other important result of this report is looking at carbon sinks. We know that we need to stop the increase of CO2 if we want to stop the temperature increase. And if we're slightly above our targets, we need to find ways to remove CO2 from the atmosphere to decrease the CO2 concentration and therefore to decrease the mean temperature on Earth. And nature has been our best ally so far, and would continue to do so. But in a low emission scenario like the 1.9, you see that the land and the ocean would take up to 70% of what we emit. Whereas in a very large emission scenario, the nature simply can't continue and keep up the pace with our emissions, which means that for every CO2 ton that is emitted, more will remain in the atmosphere and therefore be active as greenhouse gas. One other important aspect, I believe, and which is fairly new for this model, is the so-called low likelihood, high impact outcomes. It's a broader term. It includes tipping points, but it's not restricted to that. And it's, I believe, a very useful concept for policymaking, because some events might have a very low likelihood to happen given the current knowledge. But if they did, they would have such immense consequences that we might want to decide to, well, not risk going too far, even though it is not necessarily likely in the years to come. One example given here in the report is the elevation of the sea level. You can see that the different scenarios have different response, but all stay in the range of below 1 meter by 2100. However, some events, for instance, related to the West Antarctic ice sheets, we are not capable of saying how likely it actually would happen. But if it does, it would immediately make sea level rise twice as fast as even the worst scenario. And as is stated in the summary for policymakers, the higher the background level of emissions is, the higher is the likeliness that these unlikely events may happen. There are many other examples, but I don't have time to go through them all. But just to mention of the tipping points, would be the Amazon rainforest turning into a savanna, or the thawing of the Siberian permafrost. The same with the clathrates, so these ices below the sea level that also maintain methane. This aspect has been known in science for quite a long time, but as far as I can tell, it is the first time they're mentioned as clearly in an IPCC report. And you can see on these longer time scales, if you look at 2300, the difference between the various scenarios we choose are very important. 3 or 7 meters elevation or higher sea level has a huge impact for island nations, for instance. But if on top of that, some of the low likelihood but high impact events happen, this could push this elevation to, well, almost 10 meters. And that would be a completely different challenge, not just for the island nations, but for a lot of mankind. I would like to address also one point, which is a bit more technical, but which I believe is very important, in particular when thinking about the COP26. This graph, which you've probably seen, shows just that the more cumulated CO2 we emit, the warmer it gets, and it's almost a linear relationship. So based on this graph, leaders can decide how much remaining carbon budget we have before we reach net zero, according to the targets in climate change we'd like to reach and avoid further consequences. But this graph just shows the most likely results. If we look at the same picture, but in the technical summary and not in the summary for policymakers, you can see how individual models simulate this relationship between the cumulated sum of emissions and the temperature, global temperature increase. And just a back of the envelope calculation says that today we're at point A. The most best estimate for the remaining budget to reach 1.5 degrees is the arrow B, which would indeed lead us to the 1.5 level. But that's assuming that the climate sensitivity, which is indicated in the report as being the most probable, is actually true. Other sensitivities that were indicated are not the most likely, but they are physically possible. If that were the case, it means that even with policies which we believe should be fine for 1.5, could still, in the worst case, lead us to a global warming of 2 degrees. So basically, the whole idea around all the new IPCC results are not just the best estimates, but also the level of uncertainty. And therefore, basically the question, how much of a risk are we willing to take for future climate change? Thank you very much.